by scientists from leading Russian research institutes. And our primary activity fields are related with conducting research and development projects, consulting projects with different industrial partners. And also our activity includes software development for chemistry-intensive modeling and design of the technological process. Also, we provide some customer support in their own research activity when they are using our software products. Now we have a range of software products which cover different fields of science, and let me just briefly describe what we have. First of all, we have a chemical workbench. It is an integrated environment for conceptual design of physical-chemical processes and analysis of kinetic mechanisms. Chimera is a tool for calculation of the microscopic parameters of species and elementary reactions based on data coming from first principles calculations. The KinTechDB is a network-based database for accumulation of lab data on substances and processes which can be used in frame of the lab or whole organization for exchange of information between different scientists, researchers, and in general colleagues. The FDTD tool is a tool for modeling the optical properties of metamaterials and solving the Maxwell equations in complex geometries. MDKMC is an integrated environment for atomistic modeling which implements methodology of molecular dynamics and Monte Carlo simulations. And HLab is a tool for modeling and optimization of the MEMS elements fabrication based on information about the chemical processes which takes place. So let me start our general theme of this webinar, which is mechanism reduction. And first of all, let me address the question why the reduction is necessary. If we will take a look on the current fields where the chemical kinetics becomes a matter, then we should look on to combustion of real fuels, particularly it is hydrocarbon and biofuels. And of course, the final goal of using the chemical kinetic mechanisms is the CFD simulations of combustion process in real geometries of gas turbines or cylinders of internal combustion engines. And here, the main problem or bottleneck of this type of simulations, of course, is the size of kinetic mechanisms which can be used or should be used in the simulations to make these simulations predictive. And on this slide, I'm just showing how the size of the kinetic mechanism grows with length of a hydrocarbon chain. And you see that actually if we go to C8, C9, and C10 hydrocarbons, then sizes of the kinetic mechanisms for combustion becomes too large. The total number of species exceeds the 1,000, and total number of the reactions exceeds several thousands and even several tens of thousands of the reactions. And of course, it is a problem how to put these very large kinetic mechanisms into CFD codes to run the simulation of real technologies or real devices. And that is why the reduction, that is reduction of the size of the kinetic mechanisms in terms of the number of species and number of the reactions, with precise knowledge of the accuracy of the reduced mechanism with respect to detailed one, is a matter and is a very active field of research and development. To proceed to overview of our software capabilities, of course, we need to agree some terms which we will use further. And these terms are related with the types of the mechanisms which are usually used by people both in the fundamental research and engineering practice. And first of all, you should know that there is a detailed mechanism for combustion, for example, of real fuel, or if we are talking about another process, then it is a kinetic mechanism of that process. And the detailed mechanism usually consists of hundreds of species and thousands of the reactions for typical fuels. In case of the combustion of hydrocarbons fuels, it is typical single component and multi-component fuels. And usually it is supposed that these detailed mechanisms work in a wide range of the conditions. But of course, these mechanisms should be tested. The second type of the mechanisms, it is skeletal one. Usually they contain tens, maybe hundreds of species and tens and hundreds of the reactions for typical hydrocarbons fuels at least. And when we talk about the skeletal mechanism, we assume that these mechanisms are derived from the detailed one by simply removing of redundant species and reactions. Usually these mechanisms are derived for slightly narrow range of the conditions, sometimes for specific problems like ignition or laminar flame or something else. And of course, this mechanism should be tested at desired range of the conditions. They should be tested against the detailed one. The next set of the mechanism, it is reduced one, which usually contains tens of species and tens of the reactions for typical fuels. And usually these mechanisms are derived from detailed or skeletal by application of some approximations like quasi-steady state and quasi-equilibrium approximations. In most cases, these mechanisms are derived for narrow range of the conditions, and they should be tested if you would like to implement this type of the mechanisms in your simulations. And the last one type of the mechanisms is global one. It is some specific types of the mechanism just because this cannot be directly derived from all previous types. It is just a very simple of the model of the process which you consider. It can be applied in a very restricted range of the conditions, and usually just for single type of the problem. So if you will move to another type of the problem, like from ignition to laminar flames or vice versa, and will try to implement global mechanism, then with a very high probability you will fail. And of course, these mechanisms must be tested every time before the application. So when we are talking about the mechanism reduction and when we are talking about the capabilities which we have in our software, first of all, we are talking about step from detailed to skeletal mechanism. So the task for tool which we have in the frame of the chemical workbench, it is removal of redundant species and reactions from the mechanism which are not very important at the conditions which you would like to simulate and for the problem which you would like to simulate. So what is the essence of the mechanism reduction? So let's take a look on this slide where we have tried to illustrate what is the mechanism reduction. Let's assume that you have some problem which you would like to simulate and you have some targets in this problem. For example, you have the problem of laminar flame propagation and your target is simulation of the laminar flame speed. Then you have a conditions at which you need to simulate this problem. So you need to provide pressure, temperature, and composition of the reactive mixture. The last thing which is necessary for your simulation is kinetic mechanism of the chemical reactions taking place in your system. So there are three parts which you usually have for simulation of your problem. So all this information is enough to make a reduction of the initial usually large kinetic mechanism, to get smaller mechanism which can simulate the same problem with requested accuracy. And the reduction works in the following way. First of all, you need to try to solve your problem with the initial mechanism. Usually the kinetic simulation code here is used, and chemical workbench is one of the examples for these codes. And the output of this code is just kinetic curves of the process. For example, it can be the temperature profile and species profile in a homogeneous ignition problem or laminar flame problem or flow reactor if you consider some other types of the applications. And based on these kinetic curves, the reduction methods make some analysis of these curves and make conclusion about necessity of species and reactions. And if they conclude that these species or reactions are unimportant or unnecessary for your specific problem at your specific conditions, then they remove these species and reactions from the mechanism. Thus you can obtain the reduced mechanism. If we will address particularly the combustion processes, then usually there are three types of processes of interest for people. First of all, it is self-ignition, which take place in compression engines, and the problems which correspond to this type of the process, usually used by experimentalists and theoreticians, it is a shock tube or rapid compression machine or flow reactors. And people usually try to simulate the ignition delay time or profiles of species, temperature, and pressure. It depends on the problem. The second part of the problem is laminar flame, and people usually use models of Bunsen burner, a flat flame burner, or diffusion flame. And the target for the simulation is laminar flame speed, extinction limits, or profiles of the species and temperature. Why I'm addressing these problems and targets in so details? Just because for the reduction process, the specification of the problem and accurate specification of the targets is very important. So, most of the reduction methods which can generate the skeletal mechanisms from detailed ones can be divided on three basic frameworks. The first one is element or species flux analysis. The second one is time scale analysis, and the third one is sensitivity analysis. In this table, I'm just showing this approach, theoretical framework, and the examples of the methods which are already available and can be used for mechanism reduction. So, in the frame of the chemical workbench, we have implemented a tool which is called mechanism reduction module, which implements a library of state-of-the-art reduction algorithms which cover all the methodologies which I mentioned above. And this mechanism reduction module is tightly integrated with the chemical workbench. So with this tool, you have possibility to run the simulation of your specific problems. It's first. Second, reduce the mechanism with a specific reduction tool, and then test your reduced mechanism against detailed one and to estimate what is the accuracy of the mechanism. So now let me move to a short demonstration of capabilities of our mechanism reduction tool. So first of all, if you remember, every reduction starts from setup of the problem. And the problem which I would like to consider as an example, it is self-ignition of the methane at 1 atmosphere and 1,500 K, and methane is mixed with air, with a stoichiometric ratio equal 1. If I would like to set the ignition problem, then in our software there is some set of the models which correspond to this type of the problems. It is a model of calorimetric bomb reactor. It is closed homogeneous batch reactor which can be simulated at constant volume or constant pressure, and adiabatic or isothermal conditions. Now I have a setup of the model for batch reactor at constant pressure and adiabatic conditions. So in frame of my software, I have implemented this type of the model from this broad library, and have specified that initially I have stoichiometric air-methane mixture, which is initially at 1005 K degrees. And first of all, what I need to do is to run the simulation of methane ignition at specified conditions. I have already run the simulation, and here you can overview the kinetic curves as a result of the simulation. We have some species profiles in tabular form. We have a thermodynamic properties profile in tabular form, and also we have some plot how the temperature changes with time in this system. So initial mechanism is given as blue line. So I have initial ethanol mechanism for the simulation, and its prediction is given blue. The mechanism which I used in the simulation is well-known GRI 30 mechanism, which describes combustion of natural gas at high temperature conditions. My task here is to reduce this mechanism for methane self-ignition, and the requirement to the reduced mechanism is a reproduction of ignition delay time with accuracy of 5% in comparison with the original detailed mechanism. To do this, I have implemented the second project, which is just a copy of the first ethanol simulation of methane self-ignition with the same GRI 30 mechanism. I just can show you the list of the species in this mechanism. So it is 53 species as in the original GRI mechanism. And the same list of species I have here in my ethanol simulation. So what should I do next is to run the simulation with, in my second project, with original mechanism. I did this, and I have the same kinetic curves as a result of the simulation. So now the first step of the mechanism reduction is finished. I have the kinetic curves, and now I can move to reduction tool to process these curves and generate reduced mechanism. The mechanism reduction tool can be run directly from the chemical workbench, and what you have here is the following. First of all, you have a list of the reactions in the original mechanism. You have a list of the species in this mechanism, and you have a selection of different mechanism reduction methods which you can apply for mechanism reduction. These methods are for all methodologies which I have mentioned above. It is reaction path flux analysis, it is computational singular perturbation time analysis, and it is sensitivity analysis. Total, we have 10 reduction methods for implementation. As an example of mechanism reduction, I just would like to consider the directed relation graph reduction method, in which we have two types of the parameters for mechanism reduction. First of all, it is list of important species which always should be present in the mechanism. It can be adjusted by user, but usually for combustion applications, this list of the species is enough. And the second part of the second parameter of the method is just threshold value, which says which reaction paths are important and which reaction paths are not important. And to make a full reduction of my mechanism, I need to select all the time moments for my kinetic curves. And now I'm able to run the reduction method and to see what have remained in my reduced mechanism. So you can see that in my mechanism there are some reactions which are switched off, and there are some species which are switched off. Okay, so the mechanism is reduced, and now I'm able to test this mechanism against detailed one. To do this, I just need to return to chemical workbench with this reduced mechanism. And this is easily done by pressing the button Save. And now the mechanism is inside of the chemical workbench, inside of the same project. We can review this mechanism. You see that now we have a reduced number of species. Also, we have the reduced number of the reactions. And now we can run the simulation. The simulation is completed, and if we will take a look on the plot, then we will see that the reduced mechanism reproduces original simulation or prediction of the original mechanism with very good accuracy. And you can ask, can I reduce my mechanism one more time and with a different set of the parameters, and what will happen? And just a small demonstration how this can be done. I have prediction of the kinetic curves with this new mechanism. I can go back to mechanism reduction tool, select the same method, but set another value of the parameter for the mechanism reduction, select the same all time moments along the kinetic curve, run my method, generate new reduced mechanism. So with the switched off reactions, switched off species, save this mechanism back into the chemical workbench, and rerun the simulation with this new mechanism. Please take a look that this mechanism is reduced again, because now we have 38 species and smaller number of the reactions. Now we run the simulation, and let's take a look on the temperature profile. You see that we over-reduced our mechanism at given conditions just because the temperature profile have changed. So it is a matter of fact that you need to select some optimal value of the mechanism reduction parameter for your reduction. And that is the topic of the second part of our presentation devoted to best practice. To illustrate the best practice recommendations, let me consider just one specific problem which we would like to simulate. It is auto-ignition of the stoichiometric engiptane mixture given at 1 bar and in a wide range of the temperatures. For the illustration, we would like to use the kinetic mechanism of Curran, Westbrook, from Lawrence Livermore National Laboratory. And usually, if you need to simulate something, then you need to provide what is the target of your reduction and what is the desired factors. There are three general best practice recommendations for implementing the mechanism reduction in your system. First of all, a recommendation is related with stating numerical parameter for reduction method. What I mean? If you remember in the demonstration, we had some threshold value for neglecting reaction paths in the directed relation graph method. And usually there is some question, which value of this numerical parameter I need to set. And our general recommendation is the following. If you start from the initial mechanism, then please start from the relatively small value of this parameter. Then you can generate the first version of the reduced mechanism. If it's good, then you can repeat the reduction of this newly generated reduced mechanism with the same value of the parameter and get one more generation of the reduced mechanism. Usually, two-step procedure for one value of the parameter is enough, and it is illustrated in table below. Then you can increase value of the parameter and reduce the mechanism one more time, and repeat this one more time, and then it is your choice how far you need to go. The only thing you need to do every time is just test your reduced mechanism until its accuracy is lost in comparison with the detailed mechanism. The table below demonstrates how the mechanism of n-gyptane autoignition behaves with the directed relation graph method. When we set step-by-step threshold value from very small values up to relatively large value, you see that after step 1 there is significant reduction of the mechanism, but if we will apply the same value of the parameter, then the mechanism is not improved significantly. Then we can increase the parameter value and generate reduced mechanism. Here is the degree of the reduction. It is number of reactions which can be safely removed from the mechanism. And here also numbers, it is a relative error in prediction of the ignition delay times with respect to the detailed mechanism in range of the conditions which I have mentioned in our previous slide. The next question which we would like to address is the following. Usually you need to reduce, your reduced mechanism to work in the whole range of the conditions, not in a single point. Then, of course, you have a question. How many points I need to select for mechanism reduction, and how I need to generate the reduced mechanism? So maybe 1 point, or maybe several points. How much? And very good example here is just generation of the reduced mechanism which reproduces the negative temperature coefficient in low to high temperature autoignition of hydrocarbons. Our recommendation here is the following. If you will take a look on your system, in case of the autoignition and negative temperature coefficient combustion, you have 3 specific regions or ranges of the temperatures where you have different regimes of combustion. It is low temperature, it is intermediate temperature, and it is high temperature combustion. Our recommendation here is to get, first of all, to find these specific regimes of the chemical reaction in your system. Maybe it is not combustion. Then, in every range of the conditions, you need to get just 1 point. For example, this one, and this one for 3 ranges of the conditions. And then you need to generate reduced mechanism in this point, in this point, and this point. Then if you will unite these mechanisms, then you should get, let's say, final reduced mechanism which describes well the whole curve of the ignition delay time as function of the temperature in this example. Or it could be another curve in your system. And our final recommendation how to use the mechanism reduction methods is the following. Of course, you have a choice of different mechanism reduction methods. But is it possible to apply the step by step? For example, one method, then another, then a third one. And what should be the optimal strategy to apply one, second, third, and so on? And our experience shows that usually it is a good practice to start mechanism reduction from removal of the redundant species with methods which are based on connectivity analysis. For example, directed relation graph or directed relation graph with error propagation or rate of production analysis. If you will do so, then you will be able to remove significant amount of the species from the mechanism. But what is important as well is that with these species, you will remove reactions which include these species. So on first step, you are trying to remove species, but actually you remove a lot of the species and a lot of the reactions. It is a very significant step of the reduction. And as a final mechanism, you have a mechanism with species which all important for the process you need to simulate. But then maybe in your mechanism you have some reactions which are still redundant, just because their contribution to production or consumption of every important species is negligible. Then you need to apply some type of the methods which are concentrated on removal of the redundant reactions. And here we would like to mention such methods which are based on time-scale analysis, like CSP-based methods, and sensitivity analysis, like principal component analysis or principal component analysis of reaction rate matrix. And after this second step, you will be able to additionally reduce your mechanism in terms of the number of the reactions. Sometimes additional number of species is removed from this mechanism as well. So, just to conclude, it was the three best practice recommendations to apply mechanism reduction tools. I would like to say that on our website you have a capability to download our software for evaluation and to practice your problems, particularly if you have reduction problems, then you can practice it. Just because on our website we have an evaluation version of the full functionality software, and then we will be glad to hear your feedback on the software, your questions and requests related with the technical aspects. So thank you very much, and I think now we can go to questions and answers.